All right, welcome to the end of week 11. So sad, only 4 classes left. So today is your sneak preview of CS51 to give you a sense of where you can go from here on out. And even if you don't plan to continue to CS51, it will give you a sense of a very different type of programming, namely functional programming. Come Monday, we will have a similar sneak preview of CS61, a brand new course, which is another option to which you can continue next semester or in the future on systems programming. And if you like things like Problem Set 5 and Speller, our forensics problem sets, Huff and Puff, those relatively low-level implementations, do look forward to that as well. Next Wednesday, don't look forward to Quiz 2, which will be then. And then finally, our exciting conclusion and very last lecture ever will be next Friday. So a couple of announcements. We have a bunch of seminars coming up. For the definitive list, go to the bulletin board and click Announcements. And all of the TFs leading these seminars have been posting days and times and descriptions there. The most immediate are these here, a seminar by Chris Power today at 5 p.m. in Maxwell Dworkin 221. This is how to make text messaging-based programs, similar in spirit to Shuttle Boy. An IDE seminar tomorrow, also by Chris at 2 p.m. in Science Center 309A. An IDE is an integrated development environment, and think of this as nano, but much better and more powerful and versatile. Also this weekend, tomorrow, choosing the right infrastructure. Those of you guys who have a vision, you think, for what you want to do for your projects, but really aren't sure where to begin, especially with respect to the framework and design you need to. The TFs will, on tomorrow, give you a sense of what kinds of questions you should be asking and answering. Event-driven programming as well on Sunday at 12. Event-driven programming is most germane to those of you who are interested in games or more sophisticated user interfaces than the more procedural programs we've been writing. Also a seminar after that on network programming on Sunday. And then finally, if not most importantly, those of you guys considering web-based projects that you plan to do in PHP, with or without MySQL, know that you won't have to use necessarily your people.fas accounts, which is a relatively slow system, and also one that you might, in the database you have for the problem set 7 might not be something that persists for very long. The Harvard Computer Society has very kindly offered to provide any of you guys, that if you would like, with your very own HCS account, whose design will be identical to almost every student groups on campus, so these skills will be quite transferable to leading, say, your student group organization as webmaster in the future, and they'll give you PHP access, MySQL access, Ruby access, Python access, I think, and a whole bunch other stuff. Much more than you can get with your own FAS accounts. So with that said, I'm really quite pleased today to have a guest joining us. If you guys haven't yet had this sort of experience in your life, this is one of these men who, for me, has completely been a mentor, perhaps the mentor in my life, in the sense that he's given me a huge number of opportunities, primarily my first start at teaching back with the Extension School when I was an undergrad. And quite literally, he too is one of these guys without whom I would not be here today. So with that sentimental setup, let me give you Henry Leitner, Professor of Computer Science.
Thank you, David. Mentor and tormentor. You promised me hundreds and hundreds of students. Or were you referring to the online audience?
Online.
Okay. All right, then I'll just make believe we have hundreds here. Anyway, I actually taught CS51 for many, many years, probably maybe as many as 10 years, and I stopped teaching it a couple of years ago. But the course is still very much near and dear to my heart, and just by a quick show of hands, how many of you think it's within the realm of possibilities that you might take a look at CS51 in the spring? Oh, wow, good number. That's great. So what I'm going to do, as David announced, is to give you a high-level overview of what, not the essence of the entire course, but one important aspect of the course, namely functional programming. And in order to get into that, I just want to say a quick word about stuff that you've already seen, C programming, which, one way to think about it is a C program is nothing more, you can read along with me, than a web of assignment statements interconnected by control constructs, looping constructs, conditional constructs, that describe a time sequence in which they're to be executed. In some sense, then, a C program is really very close to the assembly language level. It's a higher level programming language, but it's very close to the machine level, and that's in fact how it was thought of back in the early 70s when it was first designed at Bell Laboratories. Another way of thinking about programming, or rather different sort of style of programming, is a language such as Java, which you can use as a strictly object-oriented programming language. And in that model, the view of the world is that Computation consists of the creation of quote-unquote objects, which are sent messages of various kinds to which they react. I won't get into that right now. It's an interesting paradigm. Some of you may have taken AP Computer Science in high school and may have actually experienced some of this in Java. As opposed to functional programming, exemplified by Lisp. In fact, a famous computer scientist once said there are really two kinds of programming languages out there. There's Lisp, and then there's everything else. And the reason for that statement is that in Lisp, there is only, and you'll see this firsthand in just a moment, the evaluation of an expression by function application. So the way we think about programming in Lisp is to say that instead of executing quote-unquote a program, what happens in Lisp is that we evaluate a symbolic expression. Now, Lisp is very much based upon a mathematical formalism that comes from the 1930s, which I'll speak a little bit about in a moment. But I just wanted to give you a sense of how simple the language is by actually taking a look at the language. And even though some of the details may go right past you, I think you'll get enough of a sense of the language that you may actually find it interesting and intriguing to look at even before you get into 51. Why learn Lisp? Well, there are lots of wonderful statements about the language, which you can find online. But basically, even though Lisp is a very old programming language, it's one of the earliest programming languages. It dates back to the 1950s. Over the years, there has become available a growing armamentarium of programs that exhibit what people consider to be intelligent behavior. There's a whole sub-area of computer science called artificial intelligence, which addresses problems such as natural language understanding, expert problem solving, being able to diagnose bacterial infections as good as a human physician, programs that play intelligent chess, and that sort of thing. Nearly all of these programs have been written in Lisp or in some derivative of the Lisp programming language. And so I think it's fair to say that anybody who's going to become a computer scientist needs to be at least exposed to this programming language. And if you're still not convinced, you can take a look at some examples of companies whose infrastructure is actually based upon this rather ancient programming language. If you take a look at this website, I'm not going to bother clicking the link to save time, paulgraham.com. Paul Graham, by the way, is an interesting. If you go to the website, you'll actually find a lot of wonderful essays about computer science in general. But back in, I don't know, maybe 15 years ago, he started a company in Harvard Square, which eventually was bought out by Yahoo and became the Yahoo stores. The infrastructure, if you do any shopping at yahoo.com, it's based upon the Lisp code that he and some of his Harvard buddies put together. In fact, I remember it very clearly when the company was started because he was supposed to give a guest lecture for me in CS51, and he called me the night before to apologize that he couldn't make it because he was in some serious negotiations about his company being bought out. And all I asked him at the time was, just tell me it's not Microsoft, and you're off the hook. And he said, okay, Henry, it's not Microsoft. And it turned out to be Yahoo, and he became very wealthy, as did a bunch of Harvard undergraduate and graduate students. As I said, the deep roots of Lisp date way back before the 1950s. It actually goes back to the 1920s and 30s when there were logicians and math pioneers with, I don't know if you've ever heard these names before, Alonzo Church and Skolem and Kurt Gödel, their ideas from way back then got implemented by this fellow, John McCarthy, in the 1950s. And the original description of the Lisp programming language appears in the communications of the ACM, I think looks like April 1960. I'm sure you can get it online through the Harvard Library System. So what is Lisp all about? Well, the beauty of Lisp is that you can describe its entire syntax in just 3 lines. I challenge you to find another programming language whose syntax can be described so simply. And even though the syntax is incredibly easy to define, the semantics are incredibly rich. So here we go. Lisp consists of atomic values, or atoms. They can be both numeric and they can be symbolic. In fact, let me pause for a second. Well, let me go to the next slide, and then I'll pause and actually go into Lisp so you can see. So we have atoms and we have lists of atoms. And if I just exit from this presentation for a second, I will take you to the terminal window. Actually, let me just adjust my display for a sec. And I've already launched the Lisp system. It's actually it's an interpreted language, so you don't, in fact, have to explicitly compile your programs, even though you can. So here we go. There are atoms. Atoms are things like 3.14. Those are numeric atoms. Symbolic atoms have names, such as pi, which clearly is a built-in symbolic atom. If I try typing something, though, that's not defined, such as foobar, well, we get some sort of an error message that says that's not understood. Let me get back to the top level. Second line of the definition said we have not just atoms, but we have lists of atoms. So the question is, what is a list? And the answer is, a list is anything that begins with a left paren and ends with a right paren. That's the syntax for a list. Now, that's an empty list, which is perfectly legal in Lisp. But if we want, we could put a list of meaningful atoms, such as plus 3, 4, 5, 6, 7. And what Lisp just returned, of course, is the sum of these values. So what I'm using here is prefix notation, whereas in C and in other conventional programming languages, C++, Java, and so on, arithmetic operators certainly are written in what is described as an infix form. Normally, we would think of something plus something else, whereas in Lisp, we are using prefix notation. So generally speaking, there's a function here, and then the arguments that are being applied to the function appear immediately after the name of the function. Now, what's interesting is that this could be either the name of a built-in function, the name of a user-defined function, could even be the description of a function. And one of the things I want you to get a feel for today, if nothing else, is that functions in Lisp are really, I don't know how to say this well, they're first-class objects. They can be manipulated just as easily as anything else can be manipulated in the Lisp system. The last line, I'm not going to go back to the slide right now, but the last line of the syntax definition said, we have atoms, we have lists of atoms, and then the third line says we have lists of S expressions. Now, what I was trying to define there is what Lisp means by a symbolic expression, an S expression. So if you look at the third line, what is that really suggesting? Sort of a recursive definition. What does that third line really mean? Lists of S expressions. What it really refers to is that if you look at lines 3 and 2 and how they relate to each other, what that's really saying is any one of the items in a list can itself be a list. That's right. Which means you can have expressions of the form plus together 3 with a product of 4 and 5 and 9 and 11 and, you know, the quotient of 5 and 7. Now, actually, what it just produced was a rational number, because in that context, having a slash used with 2 integers gives me, in fact, a fractional value. But in any event, what's going on here for ordinary functions in Lisp is that all of the arguments are evaluated, and then they're sent over to the function. That's true ordinarily. There are some special functions that you'll see don't evaluate all their arguments, and they would be in things like, for example, an if. A conditional function, because as you might expect, it wouldn't make sense to evaluate everything. What happens in Lisp instead is that you've got 3 arguments. There's some expression here whose value is determined to be true or false. And if the value is true, the second one of these things gets evaluated. And if it's false, the third one of the S expressions gets evaluated. So conditional execution, as opposed to evaluating everything in advance. All right, we'll come back to that in a second. Let me go back to the slides for a minute. And before you know it, we'll be able to define. Well, actually, let me stay here for a second. So we have an interpreted language. If you wanted to actually define your own function, it's really simple to do so. DEFUN is a function that helps you to define functions. Every function that you define has to have a name. So if we wanted to write a function named area of circle, I could do it like this. The next thing we put would be a list of the formal parameters, the sort of thing you might do in C. So area of a circle, we just need to know the radius. And the last thing that goes in the definition of a function is a symbolic expression whose value you're trying to compute as the value of the function. So we'll say the area of a circle is simply the result of multiplying the radius times the value of pi, which is presumably built in. Now you'll notice defining a function returned a value. Everything in Lisp is functional. It returns values. Now, the fact that the name of the function got returned is not something that's terribly useful for my purposes right now, but it could be used in another context later. Now, if you really look carefully at what I've just done here, this definition of a function is itself a list. Now, think about that for a second. What I'm suggesting here is that if the principal data type in Lisp is a list structure, and if programs themselves are list structures, then it should be the case that you can write programs in Lisp, you can define functions in Lisp that create on the fly at execution time other programs that then get evaluated. Functions creating other functions based upon knowledge of the context, knowledge of the environment in which it's in. That's why it's become such an important language in artificial intelligence. Also, the debugging tools are very rich. I won't be getting into that today, but you can trace through the execution of a function very, very straightforwardly. In any event, so having defined a function, again, without having typed anything into a file, I can simply see if this really works by asking for the area of a circle whose radius is 7.8, and without checking on it, presumably that is, in fact, the correct area. All right, so that's a very simple way of looking at things. Recursion is fundamental to the way in which Lisp does its computations. So for example, if I wanted to define a factorial function, I could do it like this. I could say factorial given an argument n is going to go through the following if. We'll simply ask the question, is it the case that the parameter n is equal to 0? And if it is, we'll return the value 1. That is, 1 is the value of the if, which becomes the value of the entire function. Otherwise, well, what is it? It's the product of the value of the parameter n times the result of computing factorial of n minus 1. You've seen recursion before, right? All right, so turns out there's a built-in function in Lisp whose name is 1 minus, whose mission in life it is simply to subtract 1 from its argument. So take the value of 1 minus n, send that to factorial. Whatever that gives you back, multiply it times n, return that from the if, which becomes the value of factorial. So factorial of 3, of course, is 6, but that's not very impressive. Factorial of 900 is impressive. So Lisp seems to allow big integers. In fact, that's more than a screenful, isn't it? Anybody want to check on that? Well, we can wait. But anyway, so Lisp is very flexible, it's very powerful, but you haven't seen nothing yet. Let me go back to the slides to reorient myself so I can see where I actually am, because I just skipped ahead a bit. Oh, my slideshow just went bye-bye. Hold on. Well, that's unfortunate. All right, hold on. I'll have to. I may have to restart the slides. Wow, hasn't done that before. Oh, phooey. All right, let's take a second. Let me just restart it. Back to Keynote. All right, anybody, while waiting for that thing to launch again, anybody have any questions at this point? I mean, I haven't shown you a great deal yet, but I have shown you at least the syntax of Lisp. Anybody here, have they seen what formal grammar rules look like? How you define? All right, I'll just throw this up for sort of for general interest, but this is something that you'll see more in CS51. When you're defining a language, whether it's say you're defining a subset of the English language, there are grammar rules. You've probably heard about them in 7th grade. You could define a sentence as consisting of a subject followed by a predicate. You know, subjects can be noun phrases. Noun phrases can consist of determiners, adjectives, nouns, proper nouns, and all that kind of thing. Programming languages, especially complicated programming languages, are also defined by formal grammar rules. And I'll just show you on this slide, I have an example of what a formal grammar for the Lisp language would be. So Lisp consists of symbolic expressions. This colon equals is grammar notation. It's a grammar rule that says a symbolic expression can be either something that's atomic or something that's a list. And the second line of the rule says a list is anything that starts literally with a left paren, ends with a right paren. And inside of those parens, this notation, S expression with a star. The star is kind of like the wildcard star that you use in the Unix operating system when you want to refer to file names consisting of any sequence of letters. That's really saying something different here. Star means 0 or more occurrences of. So it's saying a list is a sequence of 0 or more S expressions. In CS51, you'll see more of this sort of notation used. But if you read reference guides to languages, you'll very often see them expressed in terms of these grammar rules. So anyway, there we have the essence of Lisp programming. As I was saying before, in parentheses, the name or the description of a function followed by arguments. Sometimes the arguments are all evaluated. Sometimes, as in the case of if, they're not all evaluated. So parentheses must be taken very seriously. If I were to write something like, plus 3, 4, 5, perhaps sometimes in C programming, if you get a little bit unsure about the order of evaluation, you sometimes are told when you have complicated, certainly arithmetic expressions, add parentheses to make the meaning clear. If you start doing that in Lisp, though, you can really get confounded, because now it looks to Lisp as though this thing is the description of a function or the name of a function, which it's not. So adding extra parentheses is a bad idea. There are two other mechanisms that you'll see in some of my examples. Quoting with an apostrophe inhibits evaluation, and there's a built-in function named eval that does the opposite. In fact, eval is a function that's really the guts of Lisp. That is, the function named eval, when given a symbolic expression, will evaluate it. That's what Lisp ordinarily does, but you can create double and triple evaluation when needed. Another thing you'll need to know, as you see my examples, is that there's a very special atom named nil, which has a dual purpose in life. NIL means the empty list, but NIL is also an atom. It's an atomic value, and it generally means false. So just as in C, how is it? 0 means false, and anything that's non-zero can mean true in a Boolean context. In Lisp, similarly, nil means false, and anything that's non-nil would mean true. So we just defined a function. I showed you some useful built-in functions already, and we already did factorial. So let's move on. The internal representation of these list structures is the sort of thing that you've already seen before. You've already been exposed to linked lists, no doubt? Yes? All right. Well, there they are in Lisp. The linked lists consist of two halves. The left half is called CAR, and the right half is called CDR. And the reason for those acronyms is somewhat obscure. It turns out that Lisp was first implemented in the prehistoric days on an IBM 704 computer that actually had an assembly language instruction named CAR and another assembly language instruction named CDR. CAR was something like, I don't know, contents of address register, and CDR was maybe something like contents of data register, but don't quote me on that. Another way to think about these two fields is that the left-hand side gives you the first element of the list, and the second part gives you the rest of the list. So in fact, in Lisp, there's a function named CAR, and there's a synonym or an alias called first. There's a function named CDR, and there's a corresponding function named rest. You can use any of those names when manipulating list structure. So if I were to type a symbolic expression like this, you'll notice the quote mark, right? Because if I didn't put the quote mark, it would look as though I'm calling on the function foo, and I'm sending to it the value of the atom BAR. That's not what I want to do here. I'm using the quote to inhibit evaluation because I want that list structure. Foo followed by bar. Well, that's just a two-element list. There's the first element. There's the second element. And they get linked together the way they would in a C-like data structure. The slash mark means we're pointing nowhere else. That's like nil. It's like null, perhaps, in C. And then we've got foo being pointed to. We've got bar being pointed to in this fashion. So what I actually have, by having typed quote, parenthesis, foo, space, bar, right paren, that's the list structure that got created for me. That's the internal representation that Lisp has just created. This blob that says foo and this blob that says bar, those are just data structures that represent the symbolic atoms foo and bar respectively. It's that yellow arrow that's pointing down that was returned as a result of my typing quote foo space bar. So I don't actually see that internal representation. I'm just giving you the mental model of what's going on. If I were to then say, you know, I want to construct a new one of these linked list things and add something onto the front of this list structure, I could type this. I could say construct, that's another primitive function in Lisp, construct a brand new one of these, they're called dotted pairs technically, but construct another one of those with fum in the car field and that list structure, quote, foo bar in the cooter field, and that causes a third element to be added onto the list structure. And so what this cons function just returned is that pointer, the one on the far left that's going down. All right. Other Lisp functions. There are ways of doing assignment, but those create what are called side effects. And if we're really dealing with strict functional programming, you shouldn't be doing ordinary assignment a la C or a la C++ or even what you can get away with in Java. But there are functions with names like set and setf for actually assigning values to variables. So I already told you about car and cooter and cons. You can also create a list. There's a function named list for creating a list of values out of whatever. You can append two lists together. And then there are lots and lots of predicates. Because when you're dealing with conditional expressions, you may want to ask questions about whether, for example, two values are equal to each other. That is, they both point to the same object. Or whether they're numerically equal to each other. Or whether something is atomic. Or whether something is a list. Or whether something, look at number p and symbol p. That's a way of asking whether the supplied argument is numeric or symbolic, whether it's bound to a value, whether values are greater than or less than each other, and so on and so forth. So given this quick understanding of what list structures are all about, you can actually do other sorts of things. You can define, and let me just stop the presentation here so it doesn't quit on me. We can write a recursive program that computes the length of a list. Now, there's actually a built-in function named length. If I give it A, B, C, D, E, the length of the list that's returned is 4 because it's only going through the top level of the list. It's looking at the A as one element, B as another element. The third element is a sublist, and then the fourth element is E. So that's the built-in function length. If I wanted to define it for myself, it's as easy as doing factorial. I simply say, define my own version of length. I'll call it lnth for short. Given a list structure, it's again going to be a simple if statement. Except now the if statement says, I'm not talking about n being equal to 0. When you deal with list structures, what's generally the base case, the non-recursive case? What do you do with lists? Anybody? What do you check to see if the recursion should stop? If it's what? Yeah, I mean, you don't have to give it to me in list, but in English, if the list is empty, right? That's a default base case. So what I could say here, if the list is null or empty, then the length of the list is 0, right? It's an empty list. It has no length. It's not that it's null, it has a length of 0. Otherwise, it means the list consists of at least one element, so the answer is going to be it's got at least one value, plus what? Plus recursively, hello, could you compute, wow, why is this slowing? Don't do this to me. Wow. Compute the length, oh my god, I may have to restart this. No, unwired. Wow. Hold on. I'm just going to kill that session altogether. All right, so we'll define length of list as if we have an empty list, we'll give back 0. Otherwise, we'll give back 1 plus the length of what? The length of the list, but ignoring the first element, right? The length of everything else in the list. So I don't know if you remember already, but that's the rest of the list, or the cooter of the list. So give me the length of, wow, this looks like, I don't know if it's FAS? Oh, boy, these demos are going to be really tough to do. What should I do? What should I do? Are you getting? I'm on nice. Should I just kill wireless? All right. All right, so let me, all right, maybe that's what it was doing. It was doing a weak wireless signal. All right, so one more time. Nice. Here we go. This is the very last time I typed this. Define the function length. Given a list structure, if we've got an empty list, give back 0. Otherwise, give me back the length of the rest of the list. I'm sorry, so give me back, 1 plus whatever the length of the rest of the list is. That's lnth of the rest of the list. So sometimes people think LISP actually is an acronym for lots of idiotic, stupid parentheses. But in fact, it's actually, LISP is actually an acronym for list processor. It wasn't the world's first list processing language, but it was certainly the one that's most long-lived. So now the length of A, B, C, D, E, F. All right, so it's working as well as the built-in function length. There you go. All right, whew. Let's go on, and this next slide is sort of a throwaway. If anybody is interested in knowing the details of some of the most important predicates, which are easily confused, I'm just naming them here. There's a predicate, meaning a function that returns true or false, that determine if an argument is atomic, if it's a list, if it's a cons, which is a kind of a list, if it's empty, or if it's a symbol. Don't worry about the details. It's just for reference purposes for later on. So a couple more functions. Suppose I said, I want to write a function named swap. You give me a list, and I want the function to return the result of taking the first element and the second element and having them switch places. So if I gave the function swap ABCD, I want it to give me back BACD. And again, without perhaps really having a good sense for all the details, there's the definition. What it simply says is, by combining the word CAR, the function CAR, and CDR, Lisp allows you to actually just take the A's and the D's. So CADR means give me the car of the cooter. So the car of the cooter of a list would be what? If the cooter is the rest of the list without the first element, the car of the cooter is the second element, right? So splice together the second element onto a list consisting of the first element with CDDR. The cooter of the cooter means the rest of the list, means everything from the third element onward. So there's a function that would accomplish this. I'm not going to bother running it for you. Here's a numerical function. Suppose I wanted to compute the next even integer following n. I could say next even simply checks to see if the argument is even or not. And if it is, I get back n. Otherwise, I get back 1 plus the value of n. All right. The most general conditional statement of all is not if. But sometimes you have a really complicated sequence in which you want to test a symbolic expression. And if that test is true, you want to have a bunch of expressions evaluated. But if that first test is not true, you might want to have some other test. And if that test is not true, you might want to have a third test, a fourth test, a fifth test. In general, you can have as many as you want, k individual expressions, and only the one that's true will have its corresponding s expressions evaluated. I'm pointing this out because you'll see it in a couple of examples that I'm getting to very quickly. So recursion on list structures, car and cooter take lists apart. As I said, cooter is the rough analogy of taking one off from a numerical argument when you're doing recursion with an arithmetic function like factorial. So here's just another last quick example showing the use of cond. If I want, there's a built-in function named member in Lisp. If I want to ask if a value is a member of a list, I can use the built-in function. If I want to define my own, the recursive solution says something like, well, if your list is empty, we'll give back true because you've looked. Actually, we should give back false there. Sorry, that shouldn't be true. That should be nil. If the list is empty, give back nil. Sorry, that's a typo. Otherwise, if the first element in the list matches the element you're looking for, that's great. We'll give back the list from the point at which we found what we were looking for. Otherwise, search through the rest of the list recursively. But what this doesn't do, interestingly, is to go beyond the top level of the list. Just as the length function only is looking at the top level of the list structure and counting the number of elements, if you wanted to dive in more deeply, you'd have to define a function like the one that's named occurs, which is in the handout. I'm not going to go through it with you. But what that does basically is it explores at every level the cars and the quitters. So the top level of this list is at the top. But if we wanted to look for the value of B, let's say, which is down below, we would actually have to dive in recursively and not just go through the top level, but also go through the inside levels. So you'll see two levels of recursion if you take the trouble to look at that function, which again, I'm not going to spend time doing right now. Last point I want to make before I get to my two big examples is the following. Lisp, as I said, allows you to create functions on the fly, to describe functions. You can actually create an anonymous function, a nameless function. Now, this derives again back from a mathematical formalism called the lambda calculus due to Alonzo Church back in the 30s. I think he was at Princeton at the Institute for Advanced Studies. So just consider this for a second. If I said to you, look at the expression y plus x times y. I'm using standard algebraic notation here. And tell me what the value of that expression is for the values 3 and 4. What's the problem with the way I've just stated that? What's ambiguous about how I asked that question? That's right. Which is x and which is y. I haven't said is 3 bound to x and 4 bound to y, or vice versa. So among other things, Alonzo Church came up with what he described as lambda notation for getting rid of that ambiguity. And correspondingly, Lisp inherited that idea. If I show it to you for a second, I could say, here's a lambda function that takes an argument x and an argument y. And what it's going to do is it's going to add together x, I don't know if this is exactly the function I had on the previous slide, but times y and x. So that's the description of a function. And now I'm going to say evaluate it with 3 and with 4, meaning 3 is going to be bound to x because that's the first actual argument, which corresponds to the first formal parameter. Therefore, y is going to be bound to 4, which is the second argument being bound to the second formal parameter. So with those two values, we get 15. If I had done it with 4 and 3 in the opposite way, we would get 16, just because I switched the order of the arguments. So that's a pretty simple idea. And then finally, we have in Lisp the ability to do things with functions. That is, functions that take other functions as their argument. So mapcar is a wonderful example. You give it as its first argument a function of one parameter, and it'll apply that function to every value in the list. So as a quick example, if I were to say, please map the function, I showed this to you a second ago. There's a function named 1 plus, which adds 1. And apply it or map it onto the list 3, 4, -9, 11. It literally takes the function 1 plus, applies it to the value 3, gives me back 4. It applies it to the value 4, gives me back 5. As we get back a list of all of the results. So functions can take other functions as their arguments. Interesting idea. And there are actually a few other examples like that. There's a function named apply. If I had a list of values that some function handed me, a list of numbers, and I wanted to add them up, I could say something like, please apply the function plus to everything in this list, 3, 4, 9, 11, and all the values get added up. So it looks like a very straightforward idea, but it's actually pretty sophisticated relative to what you can do in other languages. So here we go. Demonstration number 1 of 2. To really understand procedural abstraction, what I'd like to do is give you in 5 minutes an introduction to the essence of Math 1B. Anybody take Math 1B? You do integration still in that course? You do integrals? All right, so let's do that in Lisp. So let's start with the following. I've got a little function named SumIntegers, which does this calculation. Starting with a value first up to a value last, it sums up all the values of n from first to last. We can write a function named SumSquares, which does the same sort of thing. It sums up the square of all values from first to last. And if I just switch to my terminal window for a second, I'm going to load in that file, sums. It's one of the ones you have in your handout. And I'm going to say, give me the sum of the integers from 1 to 10. or give me the sum of the squares of everything from 1 to 10, and there you go. And the definitions of these two functions is pretty straightforward. If you look at it, just from what I've already told you, they should be comprehensible. They're recursive, but they're very, very straightforward. So now here's the key move. What I'm going to say is, in the third point, why don't we make the function of n itself into a third parameter? In other words, if summing up functions is so important, if summing up the squares of numbers or summing up other values is so critical, why not write a function which is named SumTerms, which is given 3 arguments? It's given the name or the description of a function whose terms you want to sum up, and it's also given as its 2 other parameters, the starting point and the end point. So, for example, if I have I think there's a function named square. Let me see if there's such a thing. All right, there's a function named square, which squares its argument. I could say, give me SumTerms, pass it the function square, however that's defined, whether it's built in or whether I defined it, and give me the sum of all the squares from 1 to 10. So we get back the same number, 385, that I got when I looked at the defined function for summing up the squares. All right, so without showing you the details, just think about that for a second. SumTerms took a function as its first argument. In fact, SumTerms could even take as its argument the description of a function. In other words, I could write one of these lambda things. I could define a function on the fly and not give it a name, and it would still, as long as it returned a value, sum up all of those terms. All right, so where am I going with this? Whoops. Now let's look at something rather interesting and perhaps somewhat unexpected. Here's an infinite series that converges on the value of pi over 8. And it's written in the form 1 over 1 times 3 plus 1 over 5 times 7 plus 1 over 9 times 11. As you can imagine, the next term would be 1 over what? Right, if you look at that, you look at the pattern that's emerging, it would be 1 over what, 13 times 15. But what would be the actual pattern itself? If I wanted to define a function, without looking at the answer in the notes, if I actually wanted to define this as a pattern, what are the terms really consisting of? Anybody? In terms of n, it would be assume n is 0, where I got 1 over 1 times 3. And then n is 1 in the second term. So what have I really got here? It's 1 over something like 4n plus 1 times yeah, 4n plus 3. All right, so when n is 0, this is 1, this is 3. When n is 1, this becomes 5, this becomes 7. So in other words, it should be easy for me to define a function in Lisp which, given an argument n, returns this value. So I'm just summing up a bunch of terms. I'm not summing up squares. I'm summing up something else. So I have a function named PyTerm which computes the above. So if I take a look at PyTerm, given the value 0, it's 1/3, obviously. If I give PyTerm of 1, it's the value 1 over, what did it say, 3 times 5. Now, presumably, this is all going to converge, right, to the value pi over 8. So if I really wanted to estimate the value of pi, what I should be doing, I presume, is multiplying times 8. Now, how am I going to do this? I'm going to say sum up all the terms given the function PyTerm, and let PyTerm go from, I don't know, 0 to 30. Sum up the first 30 terms in this PyTerm thing, multiply the result by 8. Let's see if that's pi. And I didn't do that right, obviously, because I forgot the quote mark. Ha! So, sharp sign quote. PyTerm is the way you refer to functions as arguments, 0 to 30. Well, it's not very good. It's 3.12. If I say instead, no, sum up the first, I don't know, 90 terms, it's getting closer. If I say sum up the first 500 terms, 3.14. So it keeps getting better and better as we keep adding on more and more of the terms. In reality, though, I should point out this is not a good way to do this, because anybody know how real numbers are represented internally? Because of floating point imprecision, we should actually write this function in such a way that the smallest terms at the end of the sequence are being added first. This one's adding the value 1/3, and then 1 over 3 times 5, and then 1 over 5 times 7. It's the smaller ones that should be added first, but if you don't understand that, it has to do with numerical analysis and the loss of precision with real numbers. So my last step in this example is to go through the following. Is to say, given a function like f of x between the points a and b, we can compute derivatives by summing up. Here's just another summing example. Take all of those rectangles below the curve, compute their area, and add them up, and that should give you the definite integral between the points a and b of f of x. And so if you think about the width of each rectangle being dx, and by dx is going to be the width, it's going to be a uniform width, rather, for each of the rectangles, then really what we're saying is kindly sum up, if you would, from n starting at 0 to n ending at b minus a divided by dx minus 1. That's the number of rectangles, basically. So the 0th rectangle, the first rectangle, the second rectangle. In this case, there were 5 rectangles, but it could be any number of rectangles. What that's saying is evaluate the function f at the point a plus n times dx plus dx over 2. What is that really saying? It's saying if I want to compute the area of a rectangle, it's the height times the width. The width is always dx. The height of each rectangle is the value of the function at the point that's right in the middle of the rectangle. So again, think of n being 0 right now. We're asking for f of a plus dx over 2. In other words, move to the center of the first rectangle, calculate f of that. That's the height. And multiply that times dx, which is the width. Or if you just move dx out to the front, right, that's the kind of summing we want to do. And so in your notes, there's a little function named integral, which basically does this sort of summing on any function. So let me just run one example, and then we'll be almost out of time. I should have gone to my second example sooner. So if I want to take the integral of a function like, how about the integral of this function, lambda of x, which returns x? In other words, this is the function f of x, which is just x. What's the definite integral if I go from 0 to 1? What's the integral of the function x? In algebra, what's in calculus? What's the integral of x? X squared over 2, right? So I'm going to evaluate it between the points 0 and 1. So what should I get? Huh? What's x squared over 2 evaluated for the value 1 and value 0? All right, and the last argument is going to be the size of the rectangle. We get more precision if the rectangles are skinnier rather than fatter. So I don't know, I'm going to make each rectangle 0.1 in fatness. So it's 1/2, in fact. How about, let me give you one more to drive you crazy. Integral of the function square. That's the function f of x, which just gives you x squared. What's the integral of that? X to the third over 3, right? So if I evaluate this between 0 and 1 with a width, we should get back about 1/3. Or how about one last one? The integral of sharp sign quote sine, the sine function. Let me do that. Let me do that between 0 and pi. What's that going to give us? Better remember how to do that? About 2.0. All right, if you don't remember your calculus, that's fine. It doesn't matter. The last example, which I'm not going to go through, is about pattern matching. It's a fun example. If David invites me back, I will go through it. Anyway, thank you. That's it.
Thanks to Henry. We'll see you on Monday for some low-level hacking.
Low-level hacking?